Homework 2, problem 5, find the electric field for the coaxial system shown below in the three different regions, S less than A, so in this region in here, S between A and B, so in this region in between these two objects, and in the region outside the two objects. In all cases, our Gaussian surface is actually going to be a cylinder of length L. And we're going to use Gauss's law to find the electric field everywhere because we have such a nice symmetric system. Gauss's law explicitly states that the flux through the closed surface of the Gaussian surface of the electric field is equal to the volume integral of the charge density in that volume. For simplification for us, since we have a nice cylindrically symmetric system, we are going to make the statement that the electric field is going to be only in the outward S direction, pointing radially outward from the center of the cylinder. And the normal, we have going to have three normals, right? We're going to have a normal on each end cap, and that normal is going to be plus or minus z hat, and we're going to have a normal that points out of the cylinder, and that normal is going to be s hat. The surface integral of normal dot E is proportional to s hat. We said that through reasons of symmetry. So s hat dot z hat is going to give 0. So this surface integral over this closed surface is going to give us only the surface integral through the outside loop, or outside the sides of the cylinder. Furthermore, because of symmetry, and I can twist this thing however I want, the value of E is not going to change, and so the surface integral will simply give me the surface area of the outside of the cylinder times E of S at that value. So that's going to be 2 pi, the radius that we're looking at, S, times the length of the cylinder we're looking at, L, times ES as a function of S, and don't forget to stick epsilon naught in there. On the right-hand side, we have to think about which region we're in. And so if we're in the first region, we actually have to perform the integral. Luckily for us, we have a constant surface, or a constant charge density in the area of the red, and so that's going to give us the volume of a cylinder, which is pi s squared times the length times little l times our charge density in that region. And this is for S less than A. If S is greater than A but less than B, I'll simply have all the charge from the red region, and so that's the volume of the sphere, or of the cylinder, of the red cylinder. The red cylinder has radius A, so that's pi A squared times L times rho naught. And this is for A less than S less than B. And in the final region, I will have the 0, because the way the system is set up is the negative charge on the outside shell balances the positive charge on the inside solid cylinder. So this is simply going to give 0. We can easily turn this around to find that the electric field, S, as a function of S, divide both sides by 2 pi s L. The L's will cancel, the pi's will cancel, and we are going to find that this is rho naught over 2 epsilon naught. Then we're going to have S for S less than A squared divided by S for A less than S less than B, and 0 for S greater than B. And so that uniquely gives the electric field everywhere for the system. if I were to plot this, E sub s is a function of s, a and b, I'm going to find that it is linear up to a, and then this will be proportional to 1 over r squared, and then it's going to be 0 on bigger than b.